In the last chapter, we looked at how stars form from the gas between the stars, the interstellar medium, and how when they die, they return much of their mass to the ISM. Now we can go back to this idea, but focus on the other side of the story. What happens to the gas while it's in the ISM? This cycle of gas being expelled by stars and then returning to later generations of stars is known as the star-gas-star cycle. When gas is ejected from a dying star, it's extremely hot, at least thousands of Kelvin, and in the case of a supernova, it can be millions of Kelvin. However, before it can be incorporated into the next generation of stars, it has to cool off to less than 100 Kelvin. To do this, it goes through up to 6 different phases. You can think of these as being sort of like the changes water goes through when it freezes to become ice, although in this case, the ISM remains gas the entire time. It's just that in each phase, the gas behaves somewhat differently and has different temperatures and densities. Of these 6 phases, 4 have the same gas pressure, so we'll start with these ones.
That's important. A gas has space between the molecules, giving it room to contract. So depending upon pressure and temperature, a gas will have a greater or lower density. 6 phases sounds a bit complicated, but the first 4 are simply stages in the cooling process. The pressure stays constant, so as the temperature gets cooler, the density of the gas increases. This makes the gas behave somewhat differently, so we'll start by going over those differences. Afterwards, we'll go over the 2 phases of the ISM in which pressure does change, which happens for some interesting reasons directly related to the lives of stars.
The first of the main phases of the interstellar medium is called the hot ISM. This is the phase that gas is in shortly after a supernova explosion and in the strong winds produced by high-mass stars. The hot ISM is extremely hot, typically 1,000,000 Kelvin or higher, while its density is extremely low. On average, there's only 0.01 atoms per cubic centimeter. Another way of saying this is that you would only find a single atom in a volume of 100 cubic centimeters. The hot ISM is also highly ionized. Light atoms like hydrogen have lost all of their electrons, while even heavy atoms like iron have lost many of their electrons. The high temperature and extreme ionization mean that this gas produces mostly X-rays, and we can map it out using X-ray telescopes. We often find the hot ISM in the shape of spherical bubbles. Our Sun is inside one of these bubbles. Sometimes the hot gas from several supernovae can combine to form large hot regions called superbubbles. The hot ISM is also the source of an important process, the formation of cosmic rays. When a supernova explodes, shock waves along the edge of the hot ISM crash into the surrounding gas. This can accelerate ionized atoms up to nearly the speed of light. When these relativistic ions crash into the Earth's atmosphere, we call them cosmic rays, and they give us clues about what's going on in the hot ISM. The hot ISM cools by radiating X-rays out into space. As this happens, the edges change phase to the warm ISM. The warm ISM is at a temperature of 10,000 Kelvin and has a density of 1 atom per cubic centimeter. This is the most common phase in the disk of the Milky Way. The hydrogen gas in the warm ISM is mostly neutral, though some of the heavier elements can still be ionized. It's much too cool to produce any X-rays, but it does emit radio waves with a wavelength of 21 centimeters. Studying this radio light allows astronomers to map out the bulk of the galaxy's gas, as shown in the image above. As the warm ISM cools, it changes phase to form cool atomic hydrogen. Like the warm ISM, it's made mostly of neutral hydrogen, but it's much cooler and denser. The average temperature is around 100 Kelvin, and the density is about 100 atoms per cubic centimeter. Cool atomic hydrogen emits 21 centimeter radio waves, just like the warm ISM. But instead of being spread out throughout the disk, the cool hydrogen is mostly found in shells around molecular clouds. In molecular clouds, the temperature drops down to just 10 to 30 Kelvin, and the densities range from 300 to 1,000 atoms per cubic centimeter. However, the most important change comes in the nature of the hydrogen. At these temperatures and densities, atoms of hydrogen combine into molecules. A hydrogen molecule has two hydrogen atoms bound together. Molecular hydrogen doesn't emit radio waves, so it's much harder to observe than atomic hydrogen. However, wherever we find molecular hydrogen, we also find other molecules, and some of these are better emitters than hydrogen. The most important one, made of a carbon atom bound to an oxygen atom. Carbon monoxide and similar molecules emit light in the shortest part of the radio spectrum, known as microwaves. So we can map molecular clouds by mapping the locations of these microwaves. In fact, it's this microwave emission that cools molecular clouds so effectively. This image shows a carbon monoxide map of the constellation Orion, with the colors representing different densities of molecular clouds. One other way we can find molecular clouds is with dust. Many of the heavy elements, like silicon, iron, and even some of the carbon, form solid dust grains at these low temperatures. So molecular clouds are also marked by clouds of dust. Here's a map showing the same region in Orion in the far infrared. The low-temperature dust glows at these wavelengths, producing the wispy structure seen throughout the constellation. These same grains of dust look dark in visible light, as shown in these two pictures of the Horsehead Nebula. Notice the big trend that's going on here. We start with very hot hydrogen gas produced by supernovas and very hot stars. Over time, that gas cools off and goes through the warm, cool, and molecular phases, getting cooler and denser as it radiates light away. But all of this time, it keeps a constant pressure. The cool, dense molecular clouds have roughly the same pressure as the hot, low-density hot ISM. The atoms are moving a lot faster in the hot ISM, but there are a lot fewer of them in any given volume. However, in the next stage of the evolution of the ISM, that begins to change. Gravity takes over as an important force, and as a result, the pressure doesn't stay constant. This is what leads to star formation and closes the loop in the star-gas-star cycle.
Here's a table that covers the first 4 phases of the ISM. We've already put in a selection of items, but you should go back through the lecture and fill in the rest.
Most of the interstellar medium is in pressure equilibrium. As the temperature goes down, the density goes up, so that the outward push from each phase is balanced by the push it gets from the gas around it. If you multiply the temperature times the density, you get a measure of pressure, and this number is constant in most places. However, there are a few places where the gas is not in pressure equilibrium. When this happens, the gas either expands outward or collapses inward on itself. The most important collapsing phase is molecular cloud cores. In the densest regions of molecular clouds, the density can get up to over 10,000 atoms per cubic centimeter, while the temperature continues to be less than 60 Kelvin. If we just look at gas pressure, we would expect the high density would make the cloud expand. However, when we take gravity into account, we realize that the relatively high density will give the cloud core strong enough gravity to start to collapse in on itself. In the last chapter, we saw that this is the first step in the process that leads to the formation of a star, returning the gas that originally emerged from a dying star millions of years earlier. Another non-equilibrium phase of the ISM is found in star-forming regions, ionization nebulae. An ionization nebula forms when a hot O or B star forms in a star-forming region. The ultraviolet light from these stars heats up the surrounding gas to around 10,000 Kelvin and strips the electrons away from the hydrogen atoms. As the electrons recombine with the hydrogen, it starts to produce emission lines in the visible and ultraviolet parts of the spectrum, as well as a wide spectrum of radio waves. We see this as glowing ionization nebulae in star-forming regions, like the Orion Nebula in the background here. The red color from hydrogen emission is often the most obvious feature of these nebulae in visible light. All O stars produce ionization nebulae because these high-mass stars don't last long enough to get away from where they formed. Since ionization nebulae produce radio waves, we can find them even when the visible light is blocked by dust, so we can use these to get a census of all the O stars in the galaxy. In fact, there are only a few thousand of these stars out of over 200 billion stars in the Milky Way. Finally, since both the temperature and density of ionization nebulae are very high, they expand out into the surrounding space.
Now you can finish summarizing the phases of the ISM by filling in this table on the last two phases.
Now let's look at the long-term effects of the star-gas-star cycle. As we've seen, hot gas that leaves stars slowly cools through different phases of the interstellar medium until it finally turns into molecular clouds, where it collapses to form new stars. Then the stars go through their lives and return gas back to the interstellar medium. However, stellar evolution changes the nature of the gas, and this is reflected in changes in the ISM. There are two main ways the gas is changed. First, it becomes enriched in heavy elements. The first stars probably formed from gas that was just hydrogen and helium. However, nuclear fusion, along with the force of supernova explosions, create heavier elements, and these go back into the interstellar medium over time. Second, it loses gas. When most stars die, they return only part of their mass to space. The rest stays behind as white dwarfs, neutron stars, and black holes. As a result, over time, there will be less and less gas in the interstellar medium. This has implications for the stars that form as well. Since there's less gas, there will be fewer stars forming as the galaxy gets older, and these stars will have more heavy elements. We'll come back to this idea when we discuss galaxy evolution. This brings us to a way of categorizing stars by their composition. All stars are mostly hydrogen and helium, but the amount of metals in stars varies. Remember that by metals, we mean any element that isn't hydrogen or helium. The Sun and most of the stars around it are described as population 1 stars. These stars have relatively large amounts of metal in their spectra, typically 1 to 3% of the star's composition. On the other hand, some stars have only 0.1% metals. These are called population 2. Population 2 stars are generally among the oldest stars in our galaxy, and we tend to find them where we find older stellar populations, like globular clusters, and in the galactic halo. It's likely that population 2 stars formed early in the galaxy's history, before many metals had been created in stars.